Hello everyone, today I'm going to be going over the solutions for SI problem set 8 on the harmonic oscillator. Now, throughout this whole exposure to quantum mechanics that you've had so far, we've really just been giving you wave functions and you've been told to verify things. So for one, the harmonic oscillator, we gave you the ground state wave function, some constant times a Gaussian. A Gaussian is an exponential that's raised to some minus x squared power times some prefactors. Now, we may not be ready to solve the Schrodinger equation for the harmonic oscillator to reproduce this entirely by yourselves just yet, but you can actually find out what this prefactor is. It's called the normalization constant. And the way that you do that is by imposing the normalization condition. You've seen from the lectures so far that the integral of the square of the wave function should equal 1. This is something that we've seen in the lecture. Why does this have to hold? Well, we interpret the square of the wave function as a probability density. Integrating over it gives you the probability that the particle could be found between points A and B. Now, if we extend A and B to plus and minus infinity, the probability that the particle is somewhere should be 100%. So that's why we hold this relation so sacred. It conserves probability, or it tells us the probability, the total should add up to 100%. And this is actually the condition that we'll always be imposing to find our normalization condition. So you may have seen an exponential like this before in something like statistics. It kind of is like the bell curve. When we multiply by this constant, it brings it down in such a way that the total area under the curve will add up to 1. That way we can think of it as a probability distribution. Okay, so the goal for the first problem in the problem set is to find out what this normalization constant is. Yes, we've given it to you before, but you can actually reproduce it for yourselves by using an integral that will be given on certain exams, that is the Gaussian integral. The integral from minus infinity to infinity of the exponential of minus lambda x squared dx is equal to root pi over lambda. This is something you'll use a billion times, maybe more, in your lifetime. And this is integrated with respect to x. So this is supposed to be an exercise in helping you find the normalization constant for yourselves. It's great if you know this relationship, but how do you use it? And the second is getting you more familiar with Gaussian integrals. In the next problem, problem 2, we're going to take it up a notch. So try to take notes here. Okay, so if we want to impose this relationship, that tells us that the square of the wave function, we're just going to square this guy. So it's going to be n squared, which is a constant, minus infinity to infinity. If we multiply an exponential together with itself, we know that e to the a times e to the b is equal to e to the a plus b. If a and b are equal, then we just get a factor of 2. And that cancels with this guy, that factor of 2 in the denominator. Okay, so when we square the wave function here, we get an exponential of minus m omega over h bar x squared. Okay, with respect to x. Now, if we do a little bit of pattern matching here, it's always going to be a matter of massaging the integral to be in the form that we've given you the answer for a certain integral. What I mean by that is you're never going to have to solve a complicated integral from scratch. You're just going to have to put it in the form that looks like whatever we've given you. Okay? So in this case, we have that lambda by pattern matching is going to be m omega over h bar. Okay? So if we do this integral, we know that the solution should be root pi over lambda. So we have n squared times root pi over lambda. So this is just going to flip in the square root. Root pi h bar over m omega. Okay? And this should be equal to 1, because the probabilities should add up to 1. So if we just solve for n squared, we get that n squared is equal to root m omega over pi h bar. Taking the square root again just turns this 1/2 power to a 1/4, and we get that n is equal to m omega over pi h bar to the 1/4. See, we don't have to actually solve the Schrodinger equation to get this constant. To get the Gaussian, yeah, we do, but this part we can actually do just by using this little integral and this Born rule. Okay, great. Couple of quick comments on this. I never remember this ground state wave function, and if you go to higher orders, more higher excited states for the harmonic oscillator, it gets even more complicated. But you can always count on dimensional analysis to save you. So I always remember that there's at least a 2 in the denominator here. And then we know that in exponential, the argument on the inside should always be dimensionless. So whatever this constant is, if I don't remember what it is, it should have units of inverse distance squared. That way these cancel and you get something that's dimensionless. So you can always play with the dimensions. Say m has units of kilograms, omega has units of inverse seconds, and h bar has units of joule seconds, which you can decompose. And you could just play with the dimensional analysis to see what this has to be. That's always what I end up doing. Okay, that was a bit of an aside. So next we are going to move on to the more complicated question, where we're doing Fourier transforms. We're going to be dealing with problems where it may be more convenient to work in a different space than coordinate space. So let's get started on that. All right, so now we are moving on to the more challenging question out of the two, which is learning how to write functions, represent them in terms of different variables through a Fourier transform. Depending on the knowledge that you have a priori when it comes to problem solving, working in one space or another could make your problem a lot easier. If you're starting from scratch for both ends, then there's typically a conservation of effort that you have to put in. But if you do know something ahead of time, this can make things a lot smoother. And what I mean is, right now we have our wave function expressed as a function of position. But there's no inherent reason why we have to express it that way. We could maybe have it as a function of momentum instead. So when we work in terms of position, we say that it's described in a coordinate space. If we work as a function of momentum, we say that it's being described in momentum space, or it lives in a momentum space. The way that the two are connected is through what's known as a Fourier transform. So if we want to write our wave function as a function of momentum, we take the Fourier transform of the wave function in coordinate space. And there's going to be some proportionality constant, 2 pi h bar over 1 under 1 minus infinity to infinity. The wave function in terms of x times an exponential minus I on h bar p dot x, and we're integrating, so we should end up with a function that only depends on p, which means we have to add up all of the x dependence. So we integrate with respect to x. The way that I always kind of think about it is we have this wave function that's on this like x-axis, and then we're multiplying by these sines and cosines that's kind of like rotating it onto a momentum axis. If that doesn't help, then forget I just said anything. Okay, but this is the definition of the Fourier transform. This is another normalization constant that I won't make you prove or anything like that. And we want to just find out what the wave function as a function of position is. Now, the reason that we're doing this is because certain things, like if you were to calculate expectation values or averages for things like momentum, what you end up doing, like in your homework, you had to sandwich this in times the square of the wave function. And that gave you the average, like, momentum. Maybe there was a square there, I don't remember. If you're working in a coordinate space, momentum is a differential operator. Momentum in coordinate space is an operator that is minus I h bar d over dx. In coordinate space, the position operator is just a variable. So this is in coordinate space. In momentum space, the opposite happens. So in momentum space, momentum is a variable, and position becomes the differential operator. I forget what the proportionality constant is, so I'm just going to write this alpha to mean proportional to, and it's proportional to a time derivative.
Wrong.
That is
wrong. And he did the wrong thing. Wrong.
That is absolutely
wrong.
Proved over and over again.
Wrong. Wrong.
So what happens when we take these Fourier transforms is we're shifting what becomes derivatives. And this is extremely powerful because one of the things that implicitly happens with this is you get the freedom to turn differential equations into algebraic ones if you take the Fourier transform of it. And if you already know what the wave functions are in these different spaces, you've already simplified your problem a lot. So that's just looking ahead a little bit. That's a little bit of a TMI for if you want to just say, okay, no, let's just figure it out. I don't care about what I'm using it for. Then, I mean, we're done with this now. So let's start calculating stuff. Okay. So we want to calculate this Fourier transform. We're going to be using the ground state wave function for the harmonic oscillator. I'm going to call this normalization constant n, just because I don't want to carry it around the entire time. And let's get started. So again, we're going to use the fact that the product of two exponentials can be combined into one argument. Now, this problem is going to be a lot more challenging, a lot more involved than the previous one. Part of the reason for this is there's a finite number of examples I could come up with that'll make you get more used to Gaussians. This is on the more difficult end, which means any question that you could see on like exams or something would inherently have to be easier. So I figured that would probably be for the best. So let's go through it. So this is going to be equal to 1 over, actually n over root 2 pi h bar. The integral, now we're going to substitute in this exponential. So we have the exponential of minus m omega over 2 h bar x squared times the second exponential minus I on h bar p dot x. Okay, dx. And similarly, just another aside, if we had the wave function in momentum space, we could go backwards. The only thing that changes is this minus sign becomes a plus. And if you're more careful, then these also switch. These momentum and x's also switch, but it's okay. Okay, so now we're just going to combine these exponentials. So this is equal to n over root 2 pi h bar. And I'm going to factor out immediately this negative sign. So we have an exponential minus m omega over 2h bar x squared plus I on h bar p dot x dx. I'm going to switch markers because it looks like this one's getting a little tired. Okay, so there's one comment that I like to make about this. We have the x squared, we have the minus x squared, which makes it look like we can do the Gaussian integral, but we also have this linear term in x that spoils everything, or at least it seems to. So you can't automatically just use the equation for the integral for the Gaussian that we've given you in the past. We will eventually, but we have to get it into the right form first, and the way to do that is to use a mathematical tool that you probably haven't used in a million years, which is completing the square. Now, for those of you who were probably much like myself, where I don't know, I probably went on like a 5-year stint of never having to complete the square again after I learned it. So as a quick refresher, if we have, say, ax, oh, that's much nicer, ax squared plus bx, and we want to complete the square so that we just have something in terms of x all squared, we first start by factoring out the a. So that's going to be an x squared plus b over a x. So if we multiply that back out, you get back where you started. And now we're going to add something to this and subtract it right away inside of the parentheses. So we're going to add 1/2 of the square of this argument. Okay, so we're going to add that and we're going to subtract it. So that's equal to a x squared plus b over 2 squared minus b over 2a squared, and then this term again, plus b over a x, okay? And we're just going to pull the negative one outside of the parentheses. The way that we can do that is by making sure we multiply by a. So this is equal to a x squared plus b over a times x plus b squared over 4a squared minus b squared over 4a. So all I've done is I've actually squared these guys explicitly, and I brought the other one outside, the negative one outside. Okay? And if we look at this now, this is something that factors. This becomes an x plus a b over 2a. So we can write this as a x plus b over 2a squared. And then we still have this guy, minus b squared over 4a. So if we square the x, we square the b squared over that, and then we add twice of it, we get this back, multiplied by a. These guys cancel, we get back exactly where we started. So we haven't done anything, which is actually good. Okay, so this is what we're going to hold on to, and this is what we're going to put this in the form of. So this is just the work showing what the equation for completing the square is, and we're just going to be using it now. So we have, just to write it down here, we have a x plus b over 2a squared minus b squared over 4a is equal to ax squared plus bx. Okay, and that's luckily exactly what we have here. We have an a x squared plus bx. So let's go ahead and put that in the right form. So now we're just going to do a little bit of pattern matching here. We're going to find out what is what in this expression. So, and then keep in mind that we're going to end up multiplying by a minus sign at the end. Okay, so our a is equal to m omega over 2h bar. B is equal to ip over h bar. Okay, and now we're going to need b over 2a. So for 2a, the 2 cancels. So b over 2a is equal to ip over m omega. And then we also have a b squared over 4a. So b squared is going to equal minus p squared over h bar squared. And then, so that gives that b squared over 4a is equal to, where's a? A is right here. So b squared over 4a, so 4a is equal to 2m omega over h bar. B squared over 4a is then going to be minus, let's see, so we've got a minus p squared over 2m omega h bar, right? Yep, only one of those factors of h bar cancels. And this is squared p. Okay, and then we're going to end up multiplying, this is minus b squared over 4a. So all in all, we have that the integral is psi of p is equal to n over root 2 pi h bar, the integral from minus infinity to infinity, and now we have the exponential negative of this. So we have negative, what is it? M omega over 2h bar. Now our completed square term, so that's going to be an x plus b over 2a plus ip over m omega squared. Okay, so we have minus b squared over 4a, so this becomes positive, but then in the exponential we have a minus that. So this retains its minus sign. So we have minus p squared over 2m omega h bar integrated with respect to x. Now this is actually really good news because this is just a constant in the eyes of the integral because we're just integrating with respect to x, not with respect to p. So we can break up the exponential and pull it outside of the integral. Okay, so we can write this as equal to n over root 2 pi h bar, the exponential of minus p squared over 2m omega h bar, integral from minus infinity to infinity of the exponential minus m omega over 2h bar. And now what I'm going to do is I'm going to do a change of variables. We're going to let u equal x plus ip over m omega. Then du is still just equal to dx. Okay? So we can call this quantity in the exponential that's squared just u squared. And then we no longer have this term. This has been pulled outside of the integral, and we're integrating with respect to u. And finally, we have a Gaussian that we know how to work with. In this case, lambda is going to be m omega over 2h bar. So lambda over 2h bar. And I guess I erased the integral. Let's just write it up here. The integral of e to the minus lambda x squared dx is equal to root pi over lambda. So all that does is it pulls down that square root. And I'm going to substitute back in our n now. So we have a m omega over pi h bar to the 1/4. We have the 1 over root 2 pi. 1 over root 2 pi h bar. We have this exponential. And then we have this integral where lambda is m omega over 2h bar, and we can use the Gaussian integral now. So that's just going to give us another factor of root. We're going to have a 2h bar pi, so 2 pi h bar over m omega. And that's one of the beauties about the Fourier transform, is this stuff always ends up canceling. The 2 pi h bar here cancels with the 2 pi h bar here. So this is just equal to m omega over pi h bar. And then we have 1 over m omega to the 1/2, right? And then the exponential. One over m omega to the 1/2 is the same as m omega to the minus 1/2, right? 1 over m omega to the 1/2 is equal to m omega to the minus 1/2. And that's equal to m omega to the minus 2/4, right? So what we can do with that, this is to the 1/4. We can multiply this m omega to the 1/4 times this m omega to the minus 2/4, which is going to give us m omega to the minus 1/4, right? 1/4 minus 2/4 is minus 1/4. Okay, so we can just write these together by throwing the m omega in the denominator here. Okay, so this tells us that psi of p is equal to 1 over m omega pi h bar to the 1/4 times the exponential. Oops. P squared over 2m omega h bar. And there we have it. And that's all there is to it. A couple comments about this. You can go through, you can do all of the quantum mechanics in momentum space. In fact, in quantum field theory, that's kind of the common thing to do. And everything should still, the observables that you calculate, the things that you measure, should get you the same thing. So everything is completely consistent with this, and depending on the problem, it may lend itself to position or coordinate space. And all of these wave functions themselves are already documented to a bajillion excited states. So once you've done it once, you can kind of appreciate being able to look it up in a table later on. But I hope you guys found this helpful. Like I said, this is the upper bound in difficulty for these kinds of Gaussian integrals, but I thought it would highlight a couple of mathematical tools and tricks that you may not have either used before or haven't used in a long time. Either way, I hope you found it helpful, and good luck on your exam.